Today we're going to be talking about the key features of exponential functions. This should feel quite a bit like review from last unit. A lot of the terms function identically to they did in the last unit. But there is one new term that we have to talk about today. It's called end behavior. End behavior describes what the end of the functions is doing. What the ends of the functions is doing. Another way to think about that is, what do the arrows mean? I've drawn in a linear function here, and I'll demonstrate here. So we have these two arrows on the function, which mean that it goes on forever and ever in both directions. End behavior is basically describing the same thing in terms of math. Now, personally, I like to kind of think of end behavior in terms of kind of caveman speak, okay? When we talk end behavior, there will always be two statements, and I'm going to write them out like how a caveman might say them. If x get big, y gets blank. Or if x get small, y gets fill in the blank. All right, so let's go ahead, look at this linear function that we've got, and let's just talk about it like a caveman. As we move this way along the function, think about what's going to happen. Well, the function's just going to keep going. Meaning, as x gets big, y also gets big. And now think about the other end. As x moves towards negative infinity, gets smaller, the function will also get smaller. So as x gets small, y gets small as well. Now, of course, this is caveman speak. That's not good proper math. But once you understand the caveman speak version of it, the proper math follows fairly logically. We're going to take the same statement that we already wrote, but we're going to write it using symbols. If x gets big, the biggest number we know is infinity, and we're going to say as x gets big, we're going to, instead of saying get, we're going to put in an arrow. The arrow is math speak for approaches. So as x approaches infinity, y approaches whatever it approaches. Fill in the blank. Similarly, I'm going to just write it down a little bit. If x approaches negative infinity, y approaches whatever it approaches. So let's go ahead, go back to our linear function, and let's turn this from caveman speak into math speak. As x gets big, or as x approaches infinity, y also approaches infinity. Y gets big as well. Similarly, as x approaches negative infinity, it gets smaller. Y also approaches negative infinity. It gets smaller as well. So that's how it works on a linear function. Exponential functions is very much the same. We'll go ahead and look back at this particular exponential function we did the other day. Now we notice we have our two ends here. Let's go ahead and talk about the positive direction first. As x gets big, notice what will happen with the y. It'll keep going up, up, up forever. So y will also get big. We can turn that into math. As x approaches infinity, y also approaches infinity. All right. This is what I would look for in an answer. The caveman version is nice and all for understanding, but in terms of actual math, I'd want you to write it like that. All right, let's look at the other end as well. As x gets smaller, as it approaches negative infinity, y approaches, it's going to stop right there at -2. It's just going to keep going, it's going to hit that asymptote, and it's just going to keep going straight. So we could write that as math. Y approaches -2. I forgot the negative sign in front of the infinity. And it'll look something like that. All right, let's go ahead and talk about some key features for this function right here, just to make sure that we're all on the same page. All right, we'll start with the domain. In this case, the domain is going to be all real numbers. If we took that function and squished it onto the x-axis, everything would be covered. I'll give you a hint for exponential functions. More often than not, the domain is going to be all real numbers. In fact, I can't think of a case where it wouldn't be. The next thing we have to do is talk about the range. Now, the range is going to change more often because you'll notice in this case we have an asymptote. The graph doesn't go past the asymptote. So this graph has no representation for y is -3 anywhere on it. So the range is going to be from the smallest number we know about, in this case, -2, to the biggest number we know about, which would be infinity. And since -2 is an asymptote, we wouldn't invite it to the party. We would never invite the other end to the party within infinity. Let's talk the intercepts really quick. Now remember, the x-intercept is where it crosses the x-axis. Looks like to be right about there, that point. I'm going to take my best guess and say that's about -2, 0 is how you would write that ordered pair. And the y-intercept is right here. That's going to be 0, 3. Keep in mind, with asymptotes, it's possible to not have an x-intercept, and if that is the case, you can simply write NA, not applicable. I wouldn't leave it blank, though, because that just generally tells me as the teacher that you didn't know. So just write none or something like that. All right. Let's talk about increasing, decreasing, or constant. As we move across the function from left to right, I'm going to bring my ruler over. From left to right, it appears to be increasing. So this is an increasing function. And the last thing we need to know is there an asymptote on exponential functions? There will be an asymptote in this case. The asymptote is at y equals -2. Linear functions, like this one down here, don't have asymptotes. Never, ever, ever. Exponentials will always have an asymptote. Make sure that you write your asymptotes in the equation of a line. Otherwise, that is not a correct answer. As always, let me know if you have additional questions.